Okay, class. So before we get to our next exercise in the notes, I wanted to take some time to show a little bit more detail about scanning tunneling microscopes and show you a video and some recent literature. So in this video, we're going to see exactly how an STM works, and there's some captions at the bottom that I'm just going to narrate for you so you can watch the video. So if we take a look at a surface, a tunneling microscope consists of a metallic tip with an applied voltage. The tip is brought very near the surface of a metallic sample made of atoms. When the voltage is applied between the tip and the sample, electrons are extracted from the surface by quantum tunneling. This creates an electrical current between the tip and the surface. Tunneling occurs only at very short distances when the tip lies on top of an atom. By drawing the current intensity versus the tip location, one can deduce the position of the atoms of the metal surface down to a resolution better than 0.1 nanometers. So pretty amazing. And that's how we're able to get this image in the back of what a surface looks like as we move the tip around on top of the surface. So in this paper by a friend of mine from graduate school, Nicholas Talarita, who is a member of the Apicarian Lab at the University of California, Irvine, they use a scanning tunneling microscope to get a topology image of a metalloporphyrin, which is really cool. So here is some of the amazing things that you can do with a scanning tunneling microscope. So what they did is they enhanced the resolution of the STM using a single molecule of carbon monoxide absorbed onto the tip. So this is just taking a normal metal tip and adding a single molecule of CO onto it. And they were able to look at single metalloporphyrins absorbed onto a sheet of gold. So let's take a second and get a little bit of background on what we're talking about. So a metalloporphyrin is something like this. So this is an iron porphyrin. When you have an atom of a metal inside of this organic molecule called a porphyrin, you get a metalloporphyrin. So the organic part surrounding the metal is the porphyrin, and it's completely planar, and it holds the metal in place. When you have an iron porphyrin, that's called a heme. And so this is the active site of the different subunits of hemoglobin. This is also the active site of cytochrome C, which is a protein that's involved in the electron transport chain of mitochondria. So this is just a ChemDraw image of cytochrome C, the active site. But here is what the whole thing looks like, sort of in 3D, where you have these alpha helices and the active site kind of buried over there. And if you wanted to take a look at it in 3 dimensions, we can see an image of it rotating around here. So these images are based on X-ray diffractometry and putting together really big files. A cobalt porphyrin, which was used in the paper by the Apicarian Lab, involves the same type of planar organic porphyrin, but this time with an atom of cobalt in the center of it. And cobalt is different from iron in that it has this one d electron by itself in this higher energy dz squared orbital. So we have a single electron as our valence electron. And cobalt porphyrins are really useful for catalysis because of this single reactive electron. So if you had a cobalt porphyrin like this, it's reactive towards things like protons. And protons can be reduced by that single electron coming from cobalt, and you'd reduce a proton down to a hydrogen radical, and the hydrogen radical would then just couple with another equivalent of itself to produce hydrogen gas. So cobalt porphyrins are really useful in catalyzing the reduction of protons in solution to hydrogen gas that just bubbles out. So let's get back to the STM paper. So in this paper, what they're doing is they're just trying to get a topography image of that cobalt porphyrin. And here is how they do that. So here's some data from the paper. At the top, you'll see something that looks familiar. These are our cartoons showing the difference in voltage between the tip and the surface. And up here on the right, you can see a diagram of the tip and carbon monoxide couple with the gold surface. So there you have the silver tip, the single molecule of carbon monoxide absorbed onto the surface, and that Z difference right here is the distance between the CO and the surface. And what's really interesting is that we can see that the decay length is longer than the gap distance. So the decay length is shown here, and that is the decay length of the wave function. So the wave function is tunneling, traveling through space and decaying at a certain distance. And the gap distance between the CO and the surface of the gold is a few angstroms, as you can see down here. And by the time you get really close, the intensity has not dropped to zero. So there is still a certain intensity of the amplitude of the wave, showing that there is an amplitude of the wave function as you get closer to the gold. So the decay length is longer than the gap distance, which allows this tunneling and current flow to be possible. So here are the results of their experiment, where they're trying to get the topology of the cobalt porphyrin. So here in the image, we have the silver tip. Here we have the carbon monoxide that's absorbed onto that tip. Here we have the metal porphyrin, and that's absorbed onto a surface of gold. And so what they're doing is they're tunneling between the tip and CO over to the metal porphyrin that's absorbed onto the surface, and here is the topology that they get. And you can see over to the left that these are the images of the cobalt porphyrin, an actual molecule sitting on top of a sheet of gold. Now in exercise 10, we're going to take a look at how tunneling current sensitivity is related to distance. So if we assume that the current I through a barrier A is proportionate to the square of the wave function, if the difference in energy between the potential energy and total energy, so this is the remaining kinetic energy inside the barrier, is 4.50 electron volts, by what factor would the current be greater for a barrier of width 0.20 nanometers versus 0.30 nanometers? So first, we need to set this problem up. So here we have our new equation for decay of the amplitude of the wave function. And so that comes back to page 43, where we introduced that equation, where it's A coefficient times E raised to the negative kappa times position x. And again, that is the equation for decay of the amplitude of the wave function. So if we're saying that the current is proportionate to the square of the wave function, then we can set that up here. So current is going to be the wave function squared, and so that would be our coefficient A squared, and we get a 2 in our exponent for E. Now let's redefine again what kappa is equal to. That's going to be the square root of 2m times the difference in potential energy and total energy divided by h bar squared. So what we're looking for is the ratio of the current at 0.20 nanometers to the current at 0.30 nanometers. In the numerator, we have 0.20, that is the more narrow distance, and it's presumed to be greater current for a barrier that is smaller. So when we take the ratio, we have I at 0.20 over I at 0.30, and we bring in a difference in our barrier width. So our x at 0.20 nanometers and our x at 0.30. So whereas the ratio over here is a quotient, by exponent rules, a quotient becomes a difference in an exponent. So then if we bring in our value or our equation for kappa, we can substitute that into this equation to get the one at the bottom here. And so this is the equation that we're going to use on the next page. So in step 2, we will start defining some of our variables. So for us, for our decay equation, our A coefficient is just going to be equal to 1. And that is going to be given to you. The mass of an electron is seen here, 9.109 times 10 to the negative 31 kilograms. Our difference in potential energy and total energy is given to us. That's 4.50 electron volts. And what we're going to do first is convert that to joules using the ratio of 1 electron volt being equal to 1.602 times 10 to the negative 19 joules. And we can convert and discover that it's equal to 7.209 times 10 to the negative 19 joules. We have one barrier width in nanometers, 0.20, and we're going to convert that using 1 meter being equal to 10 to the 9 nanometers to being in meters, which is 2.0 times 10 to the negative 10 meters. 0.30 nanometers is just going to be equal to 3 times 10 to the negative 10 meters. And the difference between those two widths, we will find out, is negative 1 times 10 to the negative 10 meters. And finally, we just need a value for h bar squared. So h bar is equal to Planck's constant h divided by 2 pi, which is 6.626 times 10 to the negative 34 joule seconds divided by 2 pi. And when we square that, we get 1.113 times 10 to the negative 68 joule squared times second squared. So now we are in a position to solve for the ratio of current at 0.2 to our current at 0.3 nanometers. And so by plugging everything in, we have E raised to this entire amount, which is negative 2, times the square root of 2 times the mass of an electron times the difference in energy in joules divided by our value for h bar squared, times, outside of the square root, our difference in barrier width. And then when we solve, we have E raised to the negative 2, and all of those values calculate out to being equal to 1.18 times 10 to the 20th underneath the square root symbol. And here we have our units that we can cancel. So joules in the numerator cancel with joules in the denominator. Kilograms in the numerator and denominator cancel. In the denominator, seconds squared and inverse seconds squared cancel. And all that we're left with is meters squared in the denominator. And so when we get rid of all of those units, we have negative 2 times the square root of 1.18 times 10 to the 20th meters, that's an m, raised to negative 2 times their difference in distance, which ends up being negative 2 times 1.086 times 10 to the negative, or times 10 to the 10th. There's supposed to be a 10 there. Inverse meters times meters, which cancel, and we are left with a unitless value. So our ratio of current at 0.2 to our current at 0.3 nanometers is just going to be equal to E raised to the unitless 2.173, which ends up being equal to 8.78. So what does this mean? This means that the tunneling current at 0.20 nanometers is 8.78 times greater than that current at 0.30 nanometers, which makes sense. The closer that we are, the more current we observe. When we're talking about tunneling in chemical reactions, what we first need to do is take a look at a reaction coordinate diagram. So here's one where we have our y-axis is energy, and our x-axis is reaction progress. This is how the reaction progresses as it goes from reactants to products. It is not necessarily time on the x-axis, but it's similar. So as we see, the reactants start at a certain energy, they overcome some amount of activation energy, and then create a product that is at a different energy. So here, where our y-axis is actually delta H, this shows that this is an exothermic reaction. The y-axis could also be Gibbs free energy, so this could also be delta G. So in a reaction coordinate diagram, we have this portion that shows the difference in energy between the reactants and the products. This difference controls the thermodynamics of the reaction. So depending on if we're looking at delta H or delta G, this shows if it's endothermic or exothermic, endergonic or exergonic. The activation energy controls the kinetics of the reaction. So maybe this is a spontaneous reaction, but requires a certain amount of heat to get it going. So this could be a spontaneous reaction that's slow, or a spontaneous reaction that's fast. It is the activation energy that controls the kinetics of the reaction. And it is this hump, this hill here, as we go from reactants up in energy and then down to products, where tunneling comes into effect. So as we just saw for reaction coordinate diagrams, as we go from reactants to products, reactions must overcome an activation energy barrier. But tunneling can occur through this barrier. So how does that happen? First, we need to take a look at our decay length equation, which is described by 1 over kappa, and that's equal to this expression here. Now, in order for tunneling to occur, we need to keep our decay length, 1 over kappa, relatively large. Now, since we're dealing with a chemical reaction, our mass is no longer electrons, but it's much, much larger because we're going to be dealing with atoms. So if the mass in the denominator of our expression is getting larger, we need the expression V sub naught minus E to be really, really small to offset that change. And we want to keep this denominator small so that overall 1 over kappa can be large. And we can have a substantial tunneling effect. So what we're going to do is look at a ring expansion reaction. So over here on the left of our reaction coordinate diagram, we can see our reactant, which is a 4-carbon ring, seen here on the right, with a methyl group, a carbon, and a fluorine off to the side. Now, in the X-ray structure that you can see, each of the carbons has hydrogens on it, except for the carbon that's bridging with the fluorine. So what's going on there is a carbon that has a lone pair of electrons on it. Now, if there's still 1 electron from that carbon in each of these bonds, that carbon, carbon number 1 that I've labeled, actually still has 4 valence electrons. So this is not a carbanion, it is not a carbocation, it's actually what's called a carbene. So that's something that we cover in other classes, but a carbene is a neutral carbon. And so there's a radical reaction mechanism that happens here, where single electrons move and pair up with others as we break and form new bonds. Overall, we're breaking a bond between carbon 2 and carbon 5, and we're forming a bond between carbon 1 and 2, which forms a double bond, and we're forming a bond between 1 and 5, which forms our new single bond. And that can be seen here, where we have formed another bond between 1 and 2, we have formed a new bond between 1 and 5, and we've broken the bond between 2 and 5. That no longer exists. So going over to our reaction coordinate diagram, here we have our 4-membered ring as a reactant. It's supposed to go over some certain amount of activation energy and then at the end form a more stable product that is a 5-membered ring in this ring expansion. Now, how do we know that tunneling is happening in this reaction? Well, there's a certain amount of thermal energy that's required to go over this activation energy. And a certain amount of thermal energy allows people to predict a certain amount of time for this reaction to take place. Turns out the actual reaction time for this reaction is 10 raised to the 152 times faster than it's supposed to be. So based on the predicted values of how this reaction should go, this is astonishingly fast. And the only explanation for a reaction that's going that much faster than it's supposed to be is the fact that it's taking a shortcut and is not going over an activation energy at all and is kinetically a lot faster. And it's kinetically faster because it's going through a shortcut and tunneling right through that activation energy.